All right, guys. Good evening, good morning, good night, good everything. Yeah, so I just thought it is okay to make a little video about the code and all that. So as I speak, it's only for group 4 that is ready. So hopefully the rest will be ready maybe by midnight. But whatever the case may be, the whole process is still the same thing. Yeah. So let me try and explain the code as much as I can. Disclaimer, I don't know how to code. All right. So I think we're all familiar with plane stress analysis, and I'm using the 4 division as a case study. So obviously, if you know how to do the manual calculation, the manual solution, where you find your K, where you find your A, where you find your B matrix, your D matrix, and all the matrices that you can think of. If you know the steps and all that, to explain the code or even to read and understand the code shouldn't be a big deal. Yeah. So these are just some of the steps that we do in doing the manual calculation. Yeah. I'm sure everybody's familiar with this. So yeah. So back to the code itself. So this is what the code looks like. I believe you can see my screen just by this left side. This is the code, and this is the where are you? All right. So this is the manual solution. So for the 4 divisions, right? So we have a plate. So you have your plate, which is 4 sides, yeah, and it's divided into this and this, and obviously you have your node numbering. I think 1, 2, 3, 4, and 5. Yeah, I think so. Yeah. So if you check this side now, if you check this bit of the code, yeah, so you can see that the code defines the material properties. Just know that when you see a percentage, it means some sort of a segment. In your mind, just see it as a subtopic. Yeah. So this is MATLAB everywhere. Anyway, so this is MATLAB. So when you see a parenthesis, a percentage sign, just know that it's like a subtopic for easy explanation and understanding. Yeah. So first of all, they are defining the material properties. Yeah. So in this place, these are not percentage sign. They are defining the coordinates and the nodes. You understand? So like that, up to the very end. So back to what I'm saying. So they define the material properties. Obviously, we know this is the material properties given to us on the question. Secondly, we define the coordinates of the node. So like I said, we have 5 nodes, 1, 2, 3, 4, 5, and this is it over here. So if you do your math, you will get to see that, okay, yeah, this 0, 0, this is your node 1, your node 2, 0, 125. So this is it, 0, 125, and like that, if you do your X and Y coordinates. So now they are doing the element connectivity. So for the element connectivity, so this is just, it's really straightforward. So if you have your elements, we divide it into 4 elements, right? 1, 2, 3, 4. And so what this one is basically doing is how they are connected, right? So 1, 2, 3, 4. So if this is your node 1, this is node 2, this is your node 3. So the first element is 1, 2, 3. And the second element is 2, 4, 3, isn't it? So 2, 4, 3. I believe it's straightforward enough, so let's not waste time. So back to the strain displacement matrix. We know the formula of this thing, yeah? Where we have our x1, x2, x3, y1, y2, y3. We know how to calculate this thing on the manual basis, yeah? This is where the calculation is. Where is it? All this calculation, yeah? So also our area, we know how to find our area with the formula. We know what the formula is, which is, where's the formula again? A equals something, something. Yeah, this guy. A equals 1 over 2 into the matrix 1, 1, 1, x1, x2, x3, and like that. So the same thing, this is what they have here. So they've just changed the matrix, but don't be confused. It's still the same thing. So like I said, there's nothing special here. So they are just replicating the manual calculation in the code. For somebody that knows how to code, he has a way of interpreting it and putting it into code. So after that, you get your A, you know the formula for A, and you get your B matrix. What is your B matrix? You know what your B matrix is. This is the formula for B matrix. B equals to 1 over 2 into blah, 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 blah. And you have this. The same thing is here. Yeah. After then, like I said, when you have a percentage, it means like a subheading. Just take it as a subheading. So here, they are trying to what? Find the D matrix. And we know what our D matrix is from our manual calculation. From our manual calculation, where is it again? Yeah, this is it. This is the formula for D matrix. Yeah, so this is it over here. Right? So going on, element stiffness matrix, we know what that means. Basically, it's just like copy and paste. Not copy and paste in the real sense, but you know what I mean. So if you can understand the way we do this calculation manually, to do this coding or to explain the coding, I'm not saying to do it, to explain the coding to the lecturer shouldn't be a big deal. It's just following the process and just putting it in code and writing it into code. So here we have this, and then our global matrices, which is here, which is our K global equals to 2 times number of nodes times number of nodes. So I think what he has done here is to divide, we have different, let me see. So we have how many elements here? 1, 2, 3, 4. And we have how many nodes? 1, 2, 3, 4, 5. So basically what you're just trying to get is, okay, fine, I have 5 nodes. So my K global matrix at the end of the day is going to be a 10 by 10 matrix. So these are the common things that he's looking for. He's not asking you to go and say, what is the meaning of MATLAB? What is this? I believe that's what he's looking for anyways. So what else? number of nodes and elements. Yeah, so I think the code is just trying to find a way to calculate the number of nodes, which is number of nodes equals to size into node coordinates. I honestly don't know what this, but you will use idea to do it. So what else? Yeah, assembly matrix. So this place is trying to assemble all the matrices. Note that we have 4 elements, so there's going to be an individual matrix K1, K2, K3, K4, right? 4 elements, 4 individual matrices. Then your global matrix, when you match them together, because they're having 5 nodes, and you know that the degree of freedom per node is 2. 2 times 5, 10. That's your global matrix. Also, yeah, so this is where they're defining the forces that they're applying. So they're applying 10 kilonewtons at the top right. Remember the question from here. This is your 10 kilonewton. Let me see. I think there's a marker here. Yeah. So hold on. Yeah, this is your 10 kilonewton. This is your 10 kilonewton. Yeah. Yeah. So the 10 kilonewton is applied at the top right corner, which is this part. And obviously, this 10 e raised to power 3, 10 kilonewton, this is just converting it to kilonewton newton. So that one is not a big deal. What else? Apply boundary condition. So this one is basically applying boundary condition. So basically, nobody's asking you to know what write a code or learn how to write a code in a day. But it's just tactics. Like when you see a dollar sign or a percentage, I know like it's like subheading. You're trying to like tell the code to do something, right? So that's what it's going to do for this place. So this place is telling you to apply the boundary condition. All this thing is going to do at the end of the day is to what? Apply the boundary condition. So another thing here, solve for displacement. Everything here at the end of the day must what? Solve for the displacement. You understand? So anything you see under this first percentage sign is actually making sure that you are having these outputs. Yeah. And you go on and on like that. Print node numbers, coordinates, and displacement. That's self-explanatory now. So basically, this code is going to what? It's going to print the node numbers, the coordinates, and the displacement, which is what we are looking for, isn't it? And here it's saying calculate the stresses, which was in the question, the elemental stress, principal stress, and all that. What else? What else? What else? Yeah. So this one too is trying to say that we should find the elemental and the principal stress. I think it's in the question. If we have that book that I shared to us sometimes ago, I think some of us have it. Yeah, there is an example there. But mind you, this solution is not complete. So you might be wondering at some point that where are they getting this? Where are they getting this? So if you take your extra time to go and check how the thing was actually solved, you will get to know how this thing gets to play. I believe you understand. So after this, so basically this one is just trying to calculate the elemental stresses. That is what this guy is doing. So the manual calculation is in the textbook. You can go and check it out if you have the time. And if you don't have the time, I mean, it's left to you. What else? Plot the mesh. So obviously, you've said you have a plate. You have a plate of 125 by 150. So you've meshed it into 4. So what you're telling the code to do is to put it into smaller bits, right? So into 4. So your mesh must basically look like this because it's 4 rows, right? So next we have plot the undeformed mesh. Okay, this one is just trying to say, okay, at the end of the day, you want to see the relationship between the original plate and the deformed plate, isn't it? And what else? Annotate number nodes. All these ones are just paparazzi. So basically, the only thing you need to know is, okay, fine. When you see this guy, he's telling you that, okay, this is what I want. When you see this guy, he's telling you that this is what I plan to achieve with all this long drama. You understand? So just sit down for some 10, 15 minutes, just check it out. I don't think it's something really big of a thing to do. And what else? I think we've literally covered everything that needs to be covered, to be honest. I think so. So if you can solve this thing manually, this one shouldn't be an issue. The only person that will come and say he doesn't understand is the person that can't solve this. And at that point, I think it's God that can help that person at that point because we are presenting tomorrow. So what else? What else? What else? I think that's basically it. So let me just try and show you how. I think I tried running the code at some point, but let me just try and run it again just for you to have a visual representation of how that thing looks like. So this is my own MATLAB. Oh, let me clear screen. My screen is into this message. Well, that one is just by the way. Sure. Yeah, so what I've just done is just to copy the code into a new script, and then after copying the code, just run. All right. So I mean, we've copied the code, I've run the program, and this is the output. Yeah. So from here, we can see our plate. We can see the discretization is divided into 4 elements. 1, 2, 3, 4, right? So this is the graphical representation. And obviously our answers from this left side, for those of us that have been using MATLAB, for this left side, it is a little bit self-explanatory, right? So from the very on-go, like, you know that you're working with 5 nodes, isn't it? So 5 nodes, 2 displacements, 2 degree of freedom at each node. So that's 2 times 5, that's 10 degree of freedom, right? So your matrix is going to be 10 by 10, isn't it? So when you get here, from this workspace, just check. So your global matrix is 10 by 10. Can you see this? 10 by 10. Yeah. And also, I mean, I'm a little bit familiar with MATLAB. I don't know of Python, for those of us that will be using Python, but I believe it should be the same way too. So the question asks us to find what? The nodal displacement. So these are the nodal displacements. Yeah, U and V, X and Y, isn't it? So these are the nodal displacements you have at node 1, node 2, node 3, node 4, node 5. This is it all over here. These guys. And the elemental stress, your tau, your sigma X, sigma Y, and tau XY. This is what you have here. So the elemental stress was given in the calculation for the manual calculation. Some of us that have time, go and check. It's there. So you can find a way of knowing how to do that. So this is the output. So for you to say, okay, fine, let me see what my global matrix look like. Here's it again. Okay, yeah, 10 by 10. So if you click on this, if you double click, it should bring your 10 by 10 matrix. Where are you? There's a lot of stuff open on my system, so it's hanging a little bit. Yep. Yeah, so this is your 10 by 10 matrix. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is your 10 by 10 matrix, right? You can write it out if you have the time. Yeah, so, but this is your 10 by 10 matrix. And this is your K reduced. So basically, when you are trying to, how do I explain this? Okay, let's just sit down. Yeah, and this is your node coordinates. All these are 0, this 0, 1, and all those ones. This is it. And I think if you can just find something to say about this, you should be fine, to be honest. I think so. So your principal stress is, you click this one, you should bring it out. Yeah, these are your principal stresses. Yeah. 4 by 2. Obviously, you know that 4 elements. So sigma X, sigma Y, sigma X, sigma Y. So that's like 8. So that is basically it. So for those using MATLAB, this is the same explanation you're going to go through. So irrespective of the divisions, maybe 4, maybe 8, maybe 12, maybe 30, this is the same format. For those of us using Python, I don't have Python on my system yet, but I think if you run it, you should have the same output. And also for those of us that will be using Python, I think for you to run it, I'm not sure if an online editor can be able to open the Python script. So you have to download Python and maybe PyCharm. So PyCharm is just like the editor that used to do it, because I think there's a NumPy, there's a library that they used in the code that might not run on an online editor. I'm not sure. You can try it out. I'm not sure. Don't take my word as a gospel. So I'm not sure. So I think this is basically all you need to know for tomorrow. So yeah, thanks.